Hi everyone, I'm Yanfei. I'm a computer scientist at Argonne National Lab, and I work in the MPIG team. Today I'm going to talk about some of our work in optimizing the MPI shared memory communication in MPIG for modern multi-core systems. To begin with, just a little bit background of why we are interested in this. The shared memory communication in MPI is fairly simple, right? When the sender receiver two processes are on the same node, if one trying to send a message to another, uh, the uh, the intuitive efficient way would be sending the data over shared memory. Basically, one can copy the data into the memory, and the other receiver can copy the data back out. So just need a shared memory buffer in between. And it's having a high performance shared memory transport is going to significantly help with the performance. If you guys hear a cat, that's my cat. Every time I try to talk, it will thinking I'm not working. So you might have to bear with me on that. Um, yeah, so where was I? Yeah, so having a high performance shared memory communication transport is going to help with the unknown MPI performance, but more importantly, for MPI that has support for things like GPU IPC, we'll still need to use the SHMEM transport to exchange the IPC handles before the GPU can use them to read write data directly from each other. So here is what MPIG structure looks at today. So we have multiple layers, but what I want to focus on is the SHMEM mod in the blue box in the middle, which handles all the SHMEM level same transport on the same node. So we have the basic POSIX shared memory, but we also have the support for XPMM and GPU IPC. It all lives here, but both the XPMM and GPU IPC would depend on the POSIX SHMEM module to actually send the handle information across to a different process. So a little more detail about how the SHMEM communication in MPIG is done today is that we basically, for all the processes that share the same compute node, will create one big shared memory that across all of them, and each of them will have their own allocation of a free buffer. There's pre-allocated buffer with fixed size, and when the sender is trying to send a message, it will grab one of these buffer and fill in the header, the message header, and the actual data payload, and that buffer is going to be enqueued on the receiver queue on the receiver side, where the receiver would ingest all the incoming messages from the queue, and once one message has been processed, the buffer will be freed and returned back to the original free buffer pool of the sender. So what are the issues that we're facing today? So basically is we have bad performance, but particularly we have bad performance in two situations. One is we have when two processes are distributed across NUMA node, we are having trouble to get high throughput. And in addition to that, we also have a generally high message latency. This is most visible in small message, and this is actually not just across NUMA. Even within the same NUMA, we're seeing significant high overhead than what we hoped for, and then other shared memory communication like the SHMEM module inside UCX. So there's two main reasons that we're having these issues. One is largely because the existing SHMEM transport design was agnostic to the modern CPU architecture and node architecture. So we don't when we design the module is designed in a way that does not take the topology information such as which NUMA node that process lives in, and if there's any shared less level cache between them, and other information related to cache. Those are not being utilized when to optimize the shared memory communication. But apart from that, we also have some inefficient design in the transport. We have one pre-allocated, each processor have one pre-allocated buffer pool, and the receiver queue is actually using a multi-producer single consumer. So the design was largely because of the original target machine of these was Intel's Yanfei, the Knights Landing. But we'll talk about that later. So the first one is related to address the architecture related challenges. What we come up with is a topology aware shared memory communication. So as I mentioned, we are experiencing low throughput for shared memory traffic across NUMA node. This is largely because the cost of the cache coherency protocol across the link between two NUMA node is very, very expensive. And this effect has been observed in many of the system, and this also been observed in the cases where on architectures like the Intel Zen 3, where even within the one package, you have multiple CCX that doesn't share the last level cache. And then in this case, it's behave sort of similar to a NUMA node like architecture on the package, although it may not expose as different NUMA nodes. So the common solution for this is using non-temporal store to address this issue. So what non-temporal store does is basically when you so when the application perform a store operation, by default it will write to the cache, and the cache would eventually being flushed out to the memory. That is why when traffic happens across the NUMA node, it might be the cache coherency protocol trying to fetch the cache line, the updated cache line across the NUMA node. What non-temporal store gives us here is basically we can, when doing a store, we can bypass the entire cache hierarchy and directly write to the memory. In that case, then when a different NUMA node is trying to get this data, it can directly read from the memory instead of doing a cache coherence protocol and request the line across the NUMA, which in this case, reading directly from the memory is faster. And MPI has that as an option, but the problem is we don't enable them by default because it's actually can hurt the performance when two processes are within the same NUMA node. So here's a number that we get for to demonstrate this. So in here, the blue line demonstrate the performance of a regular mem copy based regular store based mem copy, and the yellow line is non-temporal store. As you can see here, for the intranode latency on the left hand and the intranuma bandwidth, in both cases, using regular store base is going to get you better performance, lower latency, and higher bandwidth. So this is why we kind of hesitated in enabling non-temporal store by default. But but we realized that the only solution that we have is to treat these two scenarios separately. So that's why there's the topology aware solution comes in. So in this case, instead of having one big shared memory region between all the processes, we're trying to separate them, separate the shared memory regions based on the locality of each process and which NUMA node that is attaching to. And so what we've been able to do is using HWLOG to detect the process binding at initialization time, and then figuring out which processes are closest together that has the shared, for example, shared last level L3 cache, or and then identify the different NUMA nodes. Of course, this would only work if the user, we were assuming the user, when launching the MPI process, is actually binding process to single core, individual cores. Otherwise, if the user is binding the process to the entire node, any cores can happen. This obviously won't get you the best performance, because the OS scheduler can move the process to any places. So what we achieve here is basically using these locality information of where the process is, and then at each communication, we'll decide whether to use a regular mem copy or a non-temporal store based mem copy. So that's the straightforward, and the performance we are getting from it is like this. So this is on a test machine that we have at the JLIC. It's the joint lab system evaluation program that we have at Argonne. We have the program offers many different machines with different architectures, and this is on one of the EPIC 3 Zen 3 machines. So as you can see here, for the baseline here again is using a regular mem copy, and but this is measuring the inter-NUMA latency and inter-NUMA bandwidth. So as you can see, using the topology aware SHMEM transport here, and they will internally switch to non-temporal store, we can significantly reduce the latency on large message, and in some cases double the available bandwidth for the communication. And similar performance can be observed on Intel's Sapphire Rapids processors, where you can see the same doubling in large message bandwidth when two processors are in different NUMA nodes. Okay, so far, any questions? Let me see. Okay, nothing in chat. Okay, so that's the topology aware SHMEM communication that handles one of the issue, which is the low bandwidth in large message across NUMA. So the next problem that we're trying to solve is the MPI's high latency shared memory communication. So generally, this for small messages. So just here a little bit background of the current SHMEM transport, the POSIX SHMEM transport. It's a module called IQ. It was named from inverse Q, but it was actually the actually implementation is no longer in inverse Q anymore. So this was introduced initially to achieve high throughputs, especially with the medium to large message, and also maintain a low memory footprint, because originally these optimization was targeted to a machine where the fast memory on the CPU was small. Thinking about Intel Nice Landing, the Yanfei architecture, where was going to be a fast MCD RAM that is closest to the CPU but limited spaces, while a majority of the memory space will be non-volatile DRAM back then. But as we all know, that architecture didn't materialize. But we were left with some of this design. So as I mentioned, each of process in this case would have a share of the entire SHMEM buffer and manage a set of pre-allocated buffer in the pool. So this buffer is currently at 16K, but it was originally at 64K, but that's not important at the moment. And then the communication part is actually implemented as a multi-producer single consumer queue. So each process will have this as a incoming message queue. When communication happens, the sender would grab a buffer from its own SHMEM buffer pool and then put the data and enqueue to this one. The issue, most of the performance issue is related to this MPSC queue implementation. So as we measure this the MPSC queue is actually implemented in a form of a linked list because it's flexible in a way that we don't have to predetermine the queue size and handling the cases where a remote process trying to write to the queue, but the queue is full. So this flexibility, however, that comes with a significant performance hit is so when we measure this, we realize the enqueuing and dequeuing operation on the MPSC linked list, let's say, is fairly high. It's about 100 to 200 nanoseconds, even if there's only two processes and only one sender. So essentially no significant tension because and to make things worse, because each process is managing its own shared memory buffer, the managing information of the free buffer. So when the receiver finished with the incoming message, it will return the buffer back to the sender, which means the sender would also need to maintain another MPSC linked list to just managing the information of the free buffer. So as you can imagine, another 100 to 200 nanoseconds to enqueue and dequeue. Part of these performance issue is coming from because we have complex and too many atomic operations. In fact, I think it's 5. It's unbounded because if there's a contention on the queue header, it will try to compare swap a couple of times. But also because of that, there's multiple cache line being accessed and being bounced between the process, all contribute to this overhead. So what we come up with is a new module called Quick Queue. We name it basically to indicate what we're trying to achieve here is low latency SHMEM communication. So the design is fairly simple. We're creating a first in first out queue pairs between each process pairs. So if so instead of having a multi-producer single consumer queue, now between all the processes is only going to be single producer, and single consumer queue, which can be implemented much efficiently and getting much higher performance. And then our implementation was basically using two counters to track where the queue head and tail are. It's called SEQ and ACK. Just it's the same meaning as the sequence and acknowledgement in the TCP protocol, TCP/IP protocol, if you would. And then the queue is fixed capacity, so it would and everything is cache aligned to avoid the force sharing and other cache related issue. So we had few design choices in making this. The overall goal is we're trying to have as least atomic operation as possible, and also trying to have a more bounded or at least more predictable performance or cost on each of the operation. So what we ended up with is, but before that, SPSC is high performance SPSC is not something new. So Facebook did that in their Folly library, and there's also this SCQ that you can get. Our queue fundamentally has no different from any of these implementations, but we do have a small one or two small tweaks that we're trying to do here and related to the MPI communication. So one of these is we're trying to reduce the number of atomic operations per per message. So if you think about this, when the sender trying to send the message, it will look at the SEQ counter and see what is the next available buffer, and if that buffer is available, it will use it for communication. But if it's not available, then it will have to look at the ACK counter and see if there's any previous communication has been completed by the receiver, so that buffer can be free and reused. Which means for the sender, it may or may not need to access the ACK. And similar case on the receiver side is that the receiver would need to read SEQ to see what are the latest, how many package incoming message are there that it need to process. And for each of them being processed, it will update the ACK counter. So as you can see, there's one of these counter is always going to be read every time, but the other it may or may not be. So we create a local, for each process, we create a local counter cache to cache those information, so we can sort of amortize some of the overhead of accessing the ACK and accessing the SEQ. So we can, for each send and receive operation, we can statistically we can have less than 2 if there's enough message. And the queue, the queues, we decide to limit the size of each queue cell to 320 bytes. It's basically 256 bytes of data plus a 64 bytes header. This is mostly because now, instead of having each process have one incoming message queue, we're going to have queue pairs between each pair of processes. So effectively, an n² number of queues that is required. So we're trying to still control the memory usage on that. And the queue capacity is adjustable at initialization time, but it is always set to power of 2, so we don't have to use a modular operation when the index wrap around. And lastly, the counter are 64 bits, and in the current implementation, I never check if they overflow because I did some calculation. If individual every process is sending a million message per second, then we'll need the application to run at least 6,600 plus day to actually have an overflow here. So I basically just made a decision that not going to check that. It's just going to keep increasing, and hopefully we don't have that long running job with MPI. So with that, here's the performance that we're getting. So this is an earlier number that we get on the Sunspot, which is a evaluation system for the Aurora supercomputer. It's using an Intel Sapphire Rapids as its host CPUs. So in this case, the blue line is our baseline, the old SHMEM implementation, and the yellow line is the quick queue. So as you can see here, comparing these two lines, as you can see, for small message, that's from 1 byte to 32 bytes, the quick queue basically getting about 30% improvements on the latency. And and if we compare to UCX, that is using UCP-AM communication, we're getting almost the same performance as what UCX is getting. And in the cases where it's larger in larger size, we're actually getting a little bit better latency on message that is 32 bytes to 4K bytes. So one of the caveat here I want to mention is because the individual cells are only up to 250 can only hold up to 256 byte of data. So if the data here is larger than the message here is larger than 256 bytes, it by default, it will try to send the message in 2 pieces or 3 pieces. But because we also have on the next slides, we have the integration of a larger buffer to handle this. So in this number, you're actually seeing the performance of those optimizations for the message that is greater than 256 bytes. So like I mentioned, the quick kill itself is only good for small message. So if you send anything greater than 256 bytes, it's going to be a huge amount of small chunks and going over network. That's not good. So we take back some of the design of the Schmann buffer pool that the IQ has. So we still get these buffer if the message size is larger than what a Q cell can hold. But instead of using the IQ receive queue to handle this, we just simply take the buffer's pointer and send that using quick queue. So essentially, you can think that it's a sort of IPC-like scenario where the positive transports is only basically handling small message and header message, and large chunk and how large chunk of data is being transferred is completely independent from that. So essentially, we can use the same. We can embed the same different kind of information. For example, if the underlying machine and OS has a CMA support, we can use the user buffer pointers in there to avoid the copy in, copy out to the Schmann buffer. And if there's a SPMAM or GPU IPC support, we can also map the user buffer and just put a handle in there and using the quick kill to do fast Schmann communication. So we have this prototype, but it's not merged into MPIC yet because we have some future work that we're currently looking at. One of the issues that we see is a asymmetric load and store bandwidth on these shared buffers. Especially this is especially related to how large the buffer is can affect the load and store bandwidth we're getting on some of CPUs. And we also need to look at how to also integrate the topology awareness into the quick queue because these two were kind of independently done optimizations. And others, we also need to look at the program, how to optimize the progress. One of the current implementation is we're adding a cache for the receiver to memorize which source process has a corresponding pre-posted receive. So it is likely those processes is going to send message to us. So when we're polling, we kind of trying to poll those process first because now we have instead of one incoming queue, we have to poll many incoming queue. So that could be another overhead. And if that more performance analysis is done, hopefully this goes into MPIC soon. And also exploring alternative ways to signal the message across the process because right now it's not a sender like actively notify the receiver that there's incoming message. It's just put it in the queue and the receiver you have to pull on that. So alternative way will be something like an interrupt, but not the real interrupt. I'm looking at the new user level interrupt feature that Intel introduced in their Sapphire Rapids. but I need to get my own machine and install a customized Linux kernel to actually trial that. So I haven't been able to do that yet. And some other takeaways and thoughts. So I mean, MPI performance over shared memory is especially the latency part is largely related to how efficiently the small message is handling. Basically, we just need a super fast small message transport, and then everything else should be working nicely with that. And now, fundamentally, I see this as sending and receiving are just moving a few cache line between different CPU cores. But since we don't have any fine-grained control of how cache line is being moved between the CPU cores, so that is actually some missed optimization opportunity there. So one of the thing I'm still experimenting is the cache line demote instruction that can instead, unlike a CL flush where it flush the entire cache line to the memory, this can sort of kick it out from the L1 and L3, but maybe leave it in the last level cache. So the process on the same that the other CPU core that share the same last level cache maybe benefit a little bit from this, but we'll have to see. Lastly, basically MPIC with Quick Kill is getting a performance that is on par with the UCX active message. But again, the UCX package interface is still it's even faster. It's getting about a 160 nanosecond round trip, which is pretty close what my hardware is capable of. That's basically the limitation. So that's all I have, and thanks everyone, and I'll happy to take questions.
We have one question in chat. Did you observe any performance issues while using NT store for smaller sizes under 2K?
Under 2K, so I'm assuming you're talking about non-temporal store for internuma in this case, right? Smaller message, smaller than 2K internuma. So we don't see significant performance issue, partially because on the implementation we only even with the non-temporal store enabled for everything, the minimal threshold is 256 because that's one AVX. That's the internal threshold. We decide not to use the non-temporal store for anything greater than 256 bytes. But again, this I did a lot of actually let me pull up this. I did a lot of experiments with different architectures, and the performance of non-temporal store is very different given the different across architectures and different cache hierarchy design. So yeah, so we basically generally we don't think we don't see it's a problem for anything smaller than 2K across. But we'll probably there's more performance studies I plan to do because I know that UCX non-temporal store was using a different strategy. I think it's for the message that is greater than 3/4 of the last level cache or L2. I don't remember which cache size was used in the calculation of threshold, but yeah, that's one direction I'm trying to get more measurement
on. Does anybody else have questions in the room or online?
I have a question. Did you happen to see the difference in implementation between what you did here in MPitch and the UCX shared memory implementation?
I didn't do a comprehensive comparison, but I looked at the code a little bit. I think the UCX shmem was using a Unix socket to notify the receiver about the incoming message. I think that's a good idea. I initially didn't think about that because I was unsure what kind of the overhead or performance that that will be. But since UCX is using that, I think it's also a thing I would like to try. And also because I was planning to use this user level interrupt, which supposedly be maybe 5-6 times faster than the Unix sock or event FD. So the problem with that is it's a new feature introduced in Intel Safari Rapids, and there's no Linux kernel support that. There's an RFC patch available, which they have. I can find out a link and share. So they have some preliminary numbers on there, and if assuming that their number is correct, this is a lot faster than the event FD, which looks pretty promising to me. So I definitely intend to try that, and also compared to other maybe event FD and other solutions.
Well, in UCX we only use it when event is required, right?
Yeah.
By default,
It's not the fast path.
yeah, it is kind of slow path for events by default, just atomic.
Maybe could also use Futex just for signaling. We use the Unix, so we can make it part of the equal set if the application needs it.
Right.
Actually, I think you can also get Futex FD.
I have another question. So with this new strategy, now you have to pull multiple queues, right?
That's right.
Which is with all these multi-core architectures, historically has been difficult to scale, because now like potentially you may end up pulling hundreds of queues. And you alluded that yes, if you have post-test receive, probably somebody expects it, but some applications have huge unexpected queues as well. So what do you think? How do you plan to deal with kind of this scaling issue?
Yeah, the scaling issue is definitely we haven't figured out a very good way to deal with that, to be honest. I have a few thoughts about this. So I think one direction, at least one kind of benchmark can maybe highlight this scalability issue is a collective, and using an MPI collective where there's all many to one or out-to-out communication patterns. Then in that case, if the progress is really become an issue and dragging the performance down. But at the same time, I was thinking, because for the collective, I will probably just implement a different set of optimized collective algorithm to directly handle those cases on shared memory. So they may or may not have to directly rely on this POSIX shmem. So yeah, we'll have to do more study on how to address that.
Okay. Does anybody else have questions in the room or online?